What do astronauts eat in space? Welcome to Space Facts to fall asleep to. Tonight, we begin with something unexpectedly fascinating: food. But not just any food. Let's float gently into orbit and open a small foil pouch labeled Space Chicken Teriyaki. That's right. This is dinner aboard the International Space Station. In the early days of spaceflight, astronauts squeezed pureed meals from aluminum tubes, like toothpaste, but filled with meat and vegetables. Yuri Gagarin, the first human in space, famously ate meat puree and chocolate sauce while orbiting Earth. It wasn't elegant, but it was revolutionary. Over the decades, NASA, Roscosmos, and now SpaceX and Blue Origin have worked to make space cuisine more palatable and even comforting. Today's astronauts enjoy a menu that includes pasta, beef stew, shrimp cocktail, oatmeal, and even cookies. Everything is carefully designed for life in microgravity. Why so much care? Because food in space isn't just about calories, it's about morale. A familiar taste can be a powerful emotional anchor when you're 400 kilometers above the Earth, floating in silence. Of course, crumbs are still the enemy. Even a tiny breadcrumb can clog a ventilation system or drift into a crew member's eye. That's why most food is vacuum sealed, freeze-dried, or thermostabilized. Water is added with a needle, and utensils are magnetic or velcroed to the tray. Salt and pepper? Only in liquid form. Powdered seasoning floats. Recently, astronauts have even started growing lettuce, radishes, and mustard greens aboard the ISS as part of research into sustainable space agriculture, a vital step if we ever want to live on Mars or explore deeper into the solar system. So yes, you can eat tortillas in space, and pudding, but not cake with candles. Each bite connects astronauts to Earth and to each other. In space, flavor is memory, and memory sometimes is the most important fuel. Why there's no up or down in space. Now that we've had a quiet moment to explore what astronauts eat, let's drift into something stranger, something we often take for granted until it disappears. Let go for just a moment. No seatbelt, no floor beneath your feet. You begin to drift, not forward, not backward, just drift. In space, direction loses meaning. There is no universal up or down. On Earth, we know which way is which because gravity pulls everything toward the center of the planet. But in orbit, that pull is gone, and so is the concept of orientation. Astronauts aboard the International Space Station often describe a strange sense of freedom and confusion. A wall becomes a ceiling, a window becomes a floor. Your body rotates without friction, without resistance, and your brain, conditioned by gravity since birth, has to unlearn everything it thought it knew. There are no ceilings inside the station, no floors either. Tools are clipped to the walls, or what looks like a wall, until someone else floats in upside down and casually calls it a desk. Even the way spaceships dock must account for the absence of verticality. Approaching modules align based on arbitrary markers, not gravitational logic. Inside, every workstation is designed to be accessed from any angle, because angles themselves are relative. This concept challenges us. It's not just a quirk of physics, it's a reminder of how much we rely on gravity to define reality. Once it's gone, so is the certainty of what's above or below. In space, you are simply between stars, turning slowly, not falling, not rising, just existing, everywhere at once. The first message ever sent from deep space. As we continue drifting, weightless and untethered, let's tune our ears to the silence and listen for the very first whisper that came from beyond our world. In 1977, NASA launched two small spacecraft, Voyager 1 and Voyager 2. Their mission was to explore the outer planets, but they were also carrying something more poetic, a golden record, a message from Earth. It was humanity's first deliberate attempt to speak into the cosmic dark. The record, designed by Carl Sagan and his team, was etched with sounds and greetings in 55 languages, music from around the world, and natural sounds like thunder, laughter, and heartbeats. There's even a recording of a kiss, all packed onto a golden disc and fastened to a spacecraft with diagrams explaining where and what we are. At the time, few believed it would ever be heard. The chance that an alien civilization would intercept the signal was almost non-existent. But it wasn't really about being heard. It was about sending something, anything, into the infinite unknown, about saying we were here. Both Voyager spacecraft are still traveling. In 2012, Voyager 1 became the first human-made object to enter interstellar space. It still transmits weak signals back to Earth. It still drifts beyond the edge of the solar system, beyond planets, beyond light pollution, carrying that fragile hello across the stars. If someone, somewhere, someday finds it, they'll hear our music, our voice, our pulse. A message sent not with the expectation of reply, but with the hope that someone is listening. And now, so are we, floating quietly in the dark, listening to what we once dared to say, and what the universe never said back. Where does Earth's atmosphere actually end? We've spoken into the void, but where exactly does that void begin? Let's glide closer to home for a moment and ask a surprisingly tricky question. Where does Earth end and space begin? You might think there's a simple answer. Maybe it's where the blue fades into black, or where gravity gives way, or where satellites start to orbit. But the truth is, no one can quite agree. The most commonly accepted boundary is called the Kármán line, sitting at an altitude of 100 kilometers, 62 miles above sea level. Cross that line and you're officially in space. It's the altitude used by the Fédération Aéronautique Internationale to award astronaut status. But NASA uses a different threshold, around 80 kilometers, 50 miles. This is where the agency considers the boundary to space for mission classification and astronaut wings. Then there are private spaceflight companies like Blue Origin, which fly suborbital missions that just barely cross that threshold, offering a few minutes of microgravity and a view of the curve of the Earth. Yet here's the catch. Earth's atmosphere doesn't end abruptly. It simply thins out and keeps thinning. There's no clean edge, no border checkpoint, just a fading presence of air. The uppermost layer, the exosphere, stretches thousands of kilometers into what we would normally call space. In fact, in 2019, scientists discovered that hydrogen atoms from Earth's exosphere extend all the way out to 400,000 kilometers beyond the orbit of the moon. Technically speaking, the moon itself might still be brushing through the edge of Earth's air. This means that the concept of where space begins is not scientific, but practical, a human construct. So next time you look up and try to imagine where the sky ends, remember, the transition isn't a step, it's a blur, a liminal space where air forgets how to be air, and Earth quietly fades into the cosmos. Can you cry in space? We've drifted to the blurry edge of Earth's breath. But what happens when emotion follows us into orbit? Let's ask something simple, almost childlike. Can you cry in space? The answer is yes. But not the way you think. Tears in space don't fall. In microgravity, they cling to your eyes, forming shimmering jelly-like domes that wobble with every blink. Instead of rolling down your cheek, they grow outward until surface tension finally breaks and the bubble of salt water floats away, carrying a tiny piece of you with it. Astronauts have talked about this. Chris Hadfield, one of the most eloquent voices from orbit, described the strange discomfort of crying in zero gravity. It's not like on Earth, he said. The tears just stay there, and they sting. Crying in space isn't just emotional, it's mechanical. Without gravity to guide them, tears don't behave. They sting the eyes, they obscure vision, and they remind you in a very physical way that you're not home. But astronauts do cry, from joy, from awe, from loneliness. Floating in silence above the world can bring intense emotional release. Imagine looking down on the Earth, a soft blue marble turning slowly below you and realizing how fragile it is and how far you've gone. Some say tears are useless in orbit. Others say they're more meaningful there than anywhere else. Even NASA has studied how microgravity affects emotion, stress, and hormonal responses. Long-duration missions, especially future flights to Mars, will rely heavily on mental resilience. Because out there in the deep black, you don't just miss your family, you miss gravity, and sometimes the simple relief of a tear falling down your cheek. So yes, you can cry in space, but your tears won't fall. They'll float, glimmering like small stars, drifting gently across your face until they vanish into the air. The hidden ocean inside Europa. After the sting of weightless tears, let's go deeper, not emotionally, but literally. Beneath layers of alien ice, somewhere far from the warmth of the sun, something stirs, and it might just be alive. Let's journey now to Europa, one of Jupiter's many moons. At first glance, it looks like a smooth, cracked shell, bright, icy, scarred by deep brown lines that stretch like veins across its surface. But what lies beneath that surface is what makes Europa extraordinary. Scientists believe that under its frozen crust, Europa hides a global ocean, a vast saltwater sea, possibly twice the volume of all the oceans on Earth combined. And this ocean is warm. Not because of the sun, it's too far away. Jupiter orbits 5 times farther from the sun than Earth. The warmth comes from tidal flexing. As Europa orbits Jupiter, it gets pulled and squeezed by the planet's gravity, generating internal heat through friction. That heat might keep the ocean liquid. And where there's liquid water, energy, and organic molecules, there's always the question, could there be life? NASA is taking that question seriously. The upcoming Europa Clipper mission, launching in the next few years, will conduct flybys to analyze the moon's surface, its magnetic field, and, hopefully, the faint plumes of water vapor that occasionally spray from cracks in the ice. These plumes could carry clues about what's hiding below. Europa has become one of the most promising locations in the solar system to search for alien life. Not intelligent life, not cities, but perhaps microbes, something ancient, slow, swimming in darkness, never seeing the stars, but living nonetheless. So as we float through this cold corner of the cosmos, remember, oceans don't only belong to Earth. Some sleep in silence beneath the ice, waiting to be heard. Why rocket? Launches always happen near the equator. From oceans trapped beneath the ice, let's rise again. Upward, still fast, explosive. Let's talk about the roar beneath our feet. Let's talk about rockets. Have you ever wondered why most rocket launches take place near the equator? Why places like Cape Canaveral in Florida, Kourou in French Guiana, or even India's Sriharikota are chosen instead of, say, somewhere in Canada or Northern Europe? The answer lies not in politics, but in physics and in the invisible spin of the Earth. You see, our planet is constantly rotating, spinning once every 24 hours. But not all points on Earth move at the same speed. At the equator, you're moving the fastest, over 1,600 kilometers per hour, just from the Earth's rotation alone. That's free speed, momentum, a natural slingshot. When you launch a rocket eastward in the same direction as Earth's spin near the equator, you get a huge boost. The rocket doesn't have to generate all the speed by itself. It borrows from the planet. That's why NASA chose Florida and why ESA built its main spaceport in French Guiana. Launching from higher latitudes means spending more fuel to fight against gravity and inertia, and in spaceflight, fuel is everything. There's another reason too: safety. Equatorial launch sites often face open ocean to the east, which gives rockets a safe corridor in case of failure. No cities or people below. And now, with SpaceX and Blue Origin designing reusable rockets and planning interplanetary travel, launch location matters more than ever. The physics haven't changed, but the ambitions have. So next time you see a rocket rising into the blue, remember, it's not just aiming up. It's riding the spin of an entire planet, using Earth's momentum to escape Earth itself. How space smells, according to astronauts. After the thunder of launch fades and the engines grow silent, what's left is something you wouldn't expect: a smell. You can't breathe in space, of course, not without a suit. But when astronauts return from a spacewalk and re-enter the airlock, the scent clings to them. It seeps into the fabric of their suits, and when they remove their helmets, it's there, waiting. So, what does space smell like? Astronauts have compared it to burnt steak, hot metal, welding fumes, gunpowder, even ozone. It's a strange mix, metallic, smoky, bitter, sharp. Some call it seared metal with a hint of raspberries. Others say it reminds them of the electrical scent left after fireworks. This smell doesn't come from space itself, which is a vacuum, but from chemical reactions. When high-energy particles from the sun and cosmic radiation strike the outer layers of a spacecraft, they create volatile compounds. These compounds cling to the surface of the suit and release into the cabin when repressurization begins. In a way, it's the smell of atoms colliding with stardust, a silent signature of the cosmos, brought home in tiny, invisible fragments. NASA has even recreated the scent on Earth to help train astronauts for the sensory strangeness of life off-world. And a few adventurous perfumers have tried to bottle it, literally, for public curiosity. One such product cheekily branded itself Ode to Space. It's fascinating, isn't it? How even in the absence of air, we find ways to carry traces of the universe back with us. Not just data, not just rocks or photographs, but experiences, smells, sensations. So the next time someone tells you space is cold and empty, remember, it has a scent, and it smells like something ancient, burned, brilliant, and alive. The quietest room on Earth, and what it has to do with space. We've talked about how space smells, but what about how it sounds? To answer that, let's leave the stars for a moment and step into a room here on Earth. A room so quiet, so deeply silent that you can hear your own heartbeat, your blood moving, your bones shifting when you tilt your head. This place exists. It's called an anechoic chamber, and the quietest one is in Minnesota, inside a lab built by Orfield Laboratories. It holds the world record for silence, reaching -9 decibels. That's quieter than outer space. In space, sound doesn't travel because there's no air, no medium. If you screamed aboard the International Space Station without your suit, no one would hear you. The vacuum doesn't care. Anechoic chambers simulate this effect in a way we can experience. They're lined with thick foam wedges that absorb nearly 100% of sound. Step inside and you'll feel unsteady because there are no echoes. Your voice sounds unnatural. Your footsteps feel wrong. Some people can't stay inside for more than a few minutes. But for NASA, these chambers serve a purpose. Space agencies use them to test equipment, microphones, instruments, even astronauts' reactions to silence. Preparing the human mind for deep space missions isn't just about muscle and math. It's about mental adaptation to nothingness. Because silence in space is not just quiet, it's absolute. And when you float outside a spacecraft, tethered only by a cable, with the stars standing still around you, silence becomes not the absence of sound, but the sound of absence. It's no surprise that many astronauts say this is what truly marks the boundary between Earth and space. Not gravity, not oxygen, but silence. Why astronaut helmets lock from the back. And now, as we near the end of tonight's journey, let's look at something small, something practical, a tiny design detail that, like so much in space, hides a story. Have you ever noticed that astronaut helmets don't lock in the front? They don't snap under the chin like motorcycle helmets or bike gear. Instead, they seal from the back, locking into the suit with a smooth rotation or latch. But why? It's not about aesthetics, it's about survival and visibility. On Earth, helmet design prioritizes mobility and ease, but in orbit or on the moon, the stakes are higher. A suit is a miniature spacecraft. It provides oxygen, pressure, temperature control, and protection from solar radiation. Every joint, every seal, every hinge must be flawless. The front of the helmet is reserved for one thing: the view. A wide, bubble-like visor offers maximum visibility, not just forward, but to the sides and even slightly downward. There's no room for bulky locking mechanisms in the field of vision. Instead, the collar of the suit becomes the anchor. The helmet locks from the back using rings, latches, or twist seals. This design also allows astronauts to put the helmet on more easily, often with assistance, and to ensure that the airtight seal sits evenly around the neck ring. If the seal fails, even by a millimeter, the result could be fatal. Modern suits used by NASA, SpaceX, and upcoming Artemis missions all follow this logic. Back-locking helmets, pressurized layers, and redundant systems, all engineered not for style, but for that unforgiving vacuum just centimeters away. So the next time you see an astronaut turning their head slowly inside a glossy dome, know that every piece of that helmet is part of a story, one told in oxygen, in silence, and in the fragile promise that it will hold. How Starship is changing spaceflight forever. And tonight, we begin not with galaxies or ancient light, but with something real, a machine, a promise, a rocket tall enough to cast a shadow on the future. High above the sands of Boca Chica, Texas, a towering silver spacecraft waits, gleaming, restless, alive with fuel and fire. This is Starship, the creation of SpaceX, the vision of Elon Musk, and perhaps the vessel that will carry us farther than any human has ever gone. At 120 meters, it's the tallest rocket ever built. But that's not why it matters. Starship is designed to be fully reusable, capable of launching, landing, refueling, and flying again. Not just once, but many times. Like an airplane, only bound for the moon, Mars, and whatever lies beyond. Every test flight is a mix of spectacle and science. Some end in brilliant fire, others in gentle landings. Each one brings us closer to a future where space isn't a rare destination, but a regular departure. Its massive cargo bay could one day carry space stations habitats, or even the first seeds of a Martian colony. Its Raptor engines, fueled by methane and oxygen, were chosen with purpose because one day we may make those fuels on Mars. NASA has already selected Starship as part of the Artemis Moon program. But the real mission goes farther, making spaceflight accessible, affordable, and maybe ordinary. So as you close your eyes tonight, imagine it lifting off, not just a rocket, but the first step across a sky we've only just begun to touch. Why satellites don't fall from the sky. Starship may soar, but not everything in orbit burns fuel or lights the sky. Let's turn now to something quieter, something that simply stays, suspended, spinning, silent. All around our planet, satellites drift at thousands of kilometers per hour. Weather satellites, communication systems, GPS, and deep space telescopes. Some the size of buses, others no bigger than a shoebox. So, why don't they fall? The simple answer is they are falling, constantly. But they're also moving forward fast enough that the Earth curves away beneath them as they fall. That balance between gravity and motion creates an endless arc, an orbit. Imagine tossing a baseball across a valley. Now imagine throwing it so fast that as it falls, the ground curves away perfectly beneath it, forever. That's how satellites stay aloft. Most satellites orbit between 200 and 35,000 kilometers above the surface. The closer they are, the faster they must move to maintain orbit. The International Space Station, for example, travels at over 28,000 kilometers per hour, circling Earth every 90 minutes. But orbits aren't eternal. Over time, especially in low Earth orbit, drag from the atmosphere, even the thin upper layers, can slow satellites down. Eventually, they fall, burning up in the atmosphere like shooting stars. This is why satellites have planned lifespans, and why deorbiting has become part of modern satellite design. Some, like SpaceX's Starlink satellites, are intentionally placed low so they naturally burn up at end of life, reducing space debris. Others, like NASA's deep space observatories, are sent far beyond Earth's pull, where they'll drift in silence long after we're gone. So next time you look up at the stars, know that hundreds, even thousands, of human-made objects are up there too, not flying, not floating, so just falling perfectly. The rocket that blew itself apart on purpose. Some objects fall with grace, others fall with thunder. Let's pause over a strange kind of space mission, one that ended not with success or failure, but with destruction by design. In the early days of rocketry, not every launch was about reaching orbit. Some were about understanding what happens when things go wrong, on purpose. One of the most dramatic examples is a test conducted by NASA in the 1960s, the Little Joe 2 escape system trial. It wasn't meant to carry a satellite or land on the moon. It was meant to explode. NASA needed to prove that astronauts could survive if a rocket failed shortly after liftoff. The solution? Strap a mock-up of the Apollo capsule to the top of a booster, launch it high into the sky, and then blow the rocket apart mid-flight. The test worked. At the moment of simulated failure, the capsule's launch escape tower fired, blasting it safely away from the exploding rocket below. It parachuted gently to the ground. Mission success. Modern rockets still embrace this idea. SpaceX, for instance, deliberately destroyed one of its Crew Dragon capsules in 2020 during an in-flight abort test. The capsule was launched atop a Falcon 9, and midway through the flight, the booster was shut down on purpose. The capsule's escape engines fired, the rocket tumbled, and Crew Dragon splashed down safely in the ocean. The point? To fail safely, to make sure again and again that if the worst happens, humans survive. It's counterintuitive, even poetic. Some of our most important moments in spaceflight have come not from reaching the stars, but from falling apart the right way. In space, safety isn't always in the launch. Sometimes it's in the exit. The first woman in space and the message she sent home. Some rockets explode to keep people safe. Others rise with quiet power, carrying not just machines, but voices that had never been heard in space before. Let's travel back to 1963 to a spacecraft called Vostok 6 and to a voice crackling softly through the radio. It belonged to Valentina Tereshkova, the first woman in space. She wasn't a test pilot. She wasn't military. She was a textile worker and a skydiver, chosen from over 400 applicants by the Soviet space program to take part in one of the boldest missions of the era. Her call sign was Chaika, seagull. For 3 days, she orbited the Earth alone, circling the planet 48 times, floating, speaking, observing. All the while, millions below had no idea whether the mission would succeed. And yet it did. She became not only the first woman in space, but the first civilian to leave the planet. Her presence shattered assumptions and set the stage for generations of women to follow. She sent messages back to Earth during her flight. One of them was simple. The sky is very dark. The Earth is blue. How wonderful it all is. Her mission was not without problems. A programming error nearly caused the capsule to fly into deep space. Tereshkova noticed, reported it, and the mistake was corrected. She didn't just survive the mission, she saved it. Since then, more than 70 women have flown in space, from engineers to scientists to commanders. But she was the first, and she did it alone. Sometimes space exploration isn't about technology or fuel or re-entry angles. Sometimes it's about the sound of one voice echoing through the void for the very first time. How SpaceX lands rockets on floating drone ships. From one orbiting pioneer to another kind of boldness, this time not in who goes to space, but in how they get there and back. Let's zoom in on a scene at sea. A gray barge drifting in the Atlantic Ocean, uncrewed, silent, and on its deck, a glowing target. Miles above, a rocket booster is falling. It was part of a Falcon 9, launched by SpaceX minutes earlier. It has already done its job, lifted cargo, or perhaps a satellite, or even a crew high above Earth. But now, it's coming home. This is one of SpaceX's most remarkable achievements, the ability to land rockets upright, gently, and reuse them, not on launch pads, but on autonomous drone ships, floating in the middle of the ocean. The names of these ships are poetic. Of course, I Still Love You. Just read the instructions. They drift into place with GPS, their decks steady despite the waves. And the booster, falling at supersonic speed, fires its engines in short bursts, slows itself down, aligns, and touches down like a feather. All of this happens without human control. It's a ballet of code, precision timing, and atmospheric physics. Before SpaceX, rocket stages were single-use. They'd burn up or crash into the sea. Each mission required a brand new booster, costing tens or even hundreds of millions of dollars. Now, some Falcon 9 boosters have flown over a dozen times, reused, repaired, relaunched, again and again. Why land at sea? Because it's efficient. Rockets can launch heavier payloads if they don't have to turn around and return to land. The drone ships simply go where the rocket's arc ends, wait, and catch it. It's one of those moments where science fiction quietly becomes fact, not with noise, but with a soft landing on water. The sound of a black hole. What it really means. We've watched rockets fall back to ships. Now let's drift into something stranger, something that shouldn't make a sound at all. Let's talk about the moment a black hole was heard. In 2003, astronomers studying the Perseus galaxy cluster noticed something odd. Using NASA's Chandra X-ray Observatory, they detected ripples, faint pressure waves, moving through the gas that surrounds the central black hole of the cluster. Waves, like sound waves. Of course, sound doesn't travel through the vacuum of space, but in this case, the cluster was filled with extremely thin, superheated gas, enough of a medium to carry a vibration. The frequency, 57 octaves below middle C, a note 1,000,000 billion times deeper than human hearing. For years, it remained a scientific curiosity. But then in 2022, NASA did something unusual. They translated those waves into sound. They used real data to shift the frequency into an audible range, letting us hear the unhearable. The result was eerie, a deep, groaning hum, like wind echoing through a cave that shouldn't exist. It became known as the sound of a black hole. Of course, it's not a recording. It's a transformation, a scientific rendering of what space might sound like if our ears could stretch across galaxies. But that doesn't make it less real. It's still a voice, rising from a place where even light cannot escape. And maybe that's the most poetic part, because for so long, black holes have represented silence, the end of sound, light, even time. But here, in this case, one of them spoke, softly, slowly, in the language of pressure and gravity, a song hidden in darkness and finally heard across the void. The spacesuit that costs more than a house. We've listened to the sound of a black hole. Now let's return to something closer, more familiar, something we've seen in every photo from space, yet hardly ever think about. Let's talk about the suit. To the untrained eye, a spacesuit might look like bulky clothing, part uniform, part protection, part tradition. But in reality, it's far more than that. It's a personal spaceship. Every modern extravehicular suit, the kind astronauts wear for spacewalks, is a miracle of engineering. It must keep the body alive in the vacuum, where temperatures can swing from minus 150 degrees Celsius to plus 120 degrees Celsius, where radiation is relentless and where the air doesn't exist. It provides oxygen, regulates temperature, monitors vital signs, and allows for controlled movement in zero gravity. It even contains its own communication systems and water-based cooling garments worn next to the skin. The cost? Roughly $150 million per unit. Yes, more than a luxury home, more than most small satellites. NASA's iconic EMU suits, used since the shuttle era, are decades old, but still in use on the International Space Station. However, they're reaching the end of their lifespan, and new suits are on the way. For the upcoming Artemis missions, NASA is working with private companies to develop next-generation suits. More agile, more adaptable, and tailored for the moon's surface, they must endure regolith dust, extreme temperature changes, and allow for longer exploration. One company, Axiom Space, is leading the charge, and the prototypes look more like science fiction than anything we've sent up before. But cost aside, the real value of a spacesuit is this. It allows a human to step into a place not meant for life and survive. So next time you see that glossy visor reflecting the stars, remember, behind it is a cathedral of systems, sensors, seals, and a fragile human heart floating quietly in the dark. Why Mars sunsets are blue. Let's pause now and imagine a sunset, not here on Earth, but on Mars. You might picture red skies turning orange, then deepening into twilight. But on the red planet, sunsets are blue, and the explanation is as strange as it is beautiful. Mars is famous for its rusty color, the result of iron oxide dust covering its surface. That same dust also fills the Martian sky. But unlike Earth, where particles scatter blue light, the fine dust on Mars scatters red light away, letting more blue light pass straight through. So as the sun sets on Mars, Its fading rays travel through a thickening layer of dust. The blue wavelengths, usually scattered in all directions here on Earth, are instead focused forward, directly toward the viewer. The result? A glowing steel blue halo around the sun as it sinks toward the Martian horizon. NASA's Curiosity and Spirit rovers have captured these otherworldly moments in photographs, and they're haunting. The landscape glows in reds and browns, but the sky turns quiet, cold, and blue. It's the opposite of what we know, a reversal of expectation, a reminder that even something as universal as a sunset is shaped by where you stand or where you drift. Blue sunsets on Mars last longer than Earth's too. The thinner atmosphere means the light bends and scatters slowly. It gives the illusion that time is stretching, that dusk is lingering, holding on. And when humans finally walk on Mars, they'll end their days in that soft cobalt twilight, standing under a dusty sky, watching the sun set into silence. So as your own eyes grow heavy tonight, imagine that final light, a blue that lives on a red world, a quiet farewell from a planet that waits. The forgotten moon missions that almost happened. Mars may offer blue sunsets, but before we ever dreamed of that sky, all eyes were on the moon. We remember Apollo 11, of course, Neil Armstrong, Buzz Aldrin, the first human steps. But fewer people know that NASA once planned to return again and again. In the original Apollo program, there weren't just 1 or 2 missions. There were plans for as many as 20. Only 17 were officially numbered, and only 6 landed on the moon. After Apollo 17 in 1972, the program ended. But what came next, or rather, what almost came next, is a story of canceled momentum. Apollo 18, 19, and 20 were all planned. They had designated crews, hardware under construction, and landing sites selected, including stunning regions like Tycho Crater and the Copernicus Highlands. These were areas with complex geology that could have rewritten what we know about the moon's formation. But by the early 70s, public interest had waned. Budgets tightened. The Vietnam War demanded resources, and some in Washington wondered, why go again? Haven't we already been? So the missions were quietly scrapped. Saturn V rockets were reassigned or turned into museum pieces. The astronauts assigned to fly them never launched. It's strange to think how close we came, how many dusty footprints could have existed, how much moon rock could have been brought home, how much science and wonder was left on the table. Today, the Artemis program is promising a return with modern spacecraft, new technology, and perhaps, this time, permanence. But in the silence between Apollo and Artemis, 3 ghosts remain, missions that never launched, but still orbit the edge of memory. And maybe one day, their names will be used again, picked up, dusted off, and finished. How the space race sparked microwave ovens. We end this journey not with rockets or planets, but with something humming quietly in your kitchen. A machine so ordinary you barely think about it, but it exists, in part, because of space exploration. The microwave oven. Its origin story begins with radar. During World War II, scientists discovered that high-frequency electromagnetic waves, microwaves, could be used to detect enemy aircraft. These systems grew more powerful and precise during the early Cold War, and their development accelerated during the space race. Engineers working on radar and communication for early satellites noticed something unusual. Microwaves could heat objects quickly. One often told story involves a scientist walking near a radar test and realizing the chocolate bar in his pocket had melted. This led to the first microwave ovens in the late 1940s. They were huge, expensive, and mostly used by restaurants or military facilities. But as space tech advanced, components became smaller, more efficient, and affordable, just like in computers and communication. By the 1970s, microwaves had entered homes, and they've never left. This is one of many space-age spin-offs, technologies created or refined in the pursuit of space travel that ended up changing daily life. Memory foam, cordless tools, freeze-dried food, even water purification systems, all of them trace back to space research. It's a reminder that space isn't just distant. It's here, in your home, in your phone, in your shoes, in every beep, every reheat, every late night snack. So as you wind down tonight, think about this. Space exploration isn't always about the stars. Sometimes it's about the things that quietly orbit your life, unseen, but born from the same dreams. How the space race sparked microwave ovens. We end this journey not with stars or planets, but with something humming quietly in the corner of your kitchen, a device you use without thinking, but one that exists, at least in part, because of space. The microwave oven. Its roots reach back to the 1940s, during the development of radar systems. While working on high-frequency equipment, an engineer named Percy Spencer noticed something strange. The chocolate bar in his pocket had melted while he stood near an active radar set. Curious, he began experimenting, eventually placing popcorn kernels near the equipment. They popped. Next, he tried an egg. It exploded. Spencer had stumbled onto a new way of heating food using microwaves, a form of electromagnetic radiation. Early microwave ovens were huge, over 5 feet tall, and extremely expensive. They were mostly used in restaurants or on military bases. But things began to change in the 1950s and 60s when the space race pushed forward miniaturization, power efficiency, and advanced electronics. The demand for compact, high-frequency systems in satellites, telemetry, and communication relays led to technological breakthroughs, many of which filtered back down to Earth. By the 1970s, Thanks in part to advances driven by NASA, the microwave oven became smaller, cheaper, and more accessible. It entered homes, offices, schools, becoming one of the most widespread spin-offs of the space age. And it's not alone. Other technologies born from or accelerated by space research include memory foam, freeze-dried food, infrared thermometers, scratch-resistant lenses, and even the humble cordless drill developed for use on the moon. When we imagine the legacy of space exploration, we often picture rovers and telescopes. But sometimes its influence is closer, heating soup at midnight or thawing leftovers after a long day. A quiet revolution hiding in plain sight. So as your thoughts drift into orbit, remember, the cosmos touches more than the sky. Sometimes it hums behind a kitchen door. What Alpha Centauri might really look like. Just over 4 light-years away, drifting in the southern sky, is a system called Alpha Centauri. From Earth, it looks like a single bright star. But it's not. It's 3 stars. 2 of them, Alpha Centauri A and B, orbit each other in a tight gravitational dance, exchanging heat and light in a kind of stellar slow motion. The third, a dim red dwarf named Proxima Centauri, drifts on the outskirts, small and quiet, but potentially the most important. That's because Proxima Centauri is home to at least 2 planets, one of which, Proxima B, lies in the habitable zone, a place, at least in theory, where liquid water could exist, where a sky might glow with 2 suns, where shadows cross in curves instead of lines. We don't know what Proxima B looks like. We've never seen it. It was discovered by watching how its star wobbled, the gravitational fingerprint of something circling nearby. No telescope has captured its surface, no probe has flown past, and yet it has already captured our imagination. Projects like Breakthrough Starshot are exploring ways to reach Alpha Centauri within our lifetime, using tiny spacecraft with light sails pushed by Earth-based lasers to a fraction of light speed. If that ever happens, we might finally see it, not in pixels, but in light, not as a question, but as a place. So as you close your eyes tonight, imagine this: a world orbiting a quiet red star 4 light-years away, a second sky, a second chance, and perhaps a second home. How do space telescopes actually work? We just imagined a world orbiting another sun, but how do we know such places even exist? To answer that, we have to look not with our eyes, but with instruments built to extend them far beyond Earth. We have to talk about space telescopes. Unlike ground-based observatories, which peer up through our thick, shifting atmosphere, space telescopes float above the weather, above clouds, above distortion, above the haze of light that Earth can't help but create. They see more clearly, more deeply, and often in wavelengths of light our eyes can't perceive, like infrared, ultraviolet, and X-rays. But how do they actually work? Most space telescopes, including Hubble, Spitzer, and Chandra, use mirrors, not lenses. These mirrors collect and focus faint light from distant stars, galaxies, and nebulae. The larger the mirror, the more light it can gather, and the farther it can see. The process is delicate. Light enters the telescope's main aperture, strikes a curved mirror, and is directed toward a secondary mirror and then onto a detector, like a digital camera. But instead of snapshots, it collects long exposures over hours, sometimes days. Each photon that arrives has traveled for thousands or even billions of years. In some cases, what we're seeing is no longer there. We're observing light's memory. And space telescopes aren't just passive observers. They're built for specific missions. Some study black holes, others hunt for exoplanets, some map cosmic microwave background radiation, remnants of the Big Bang. Each one a tool designed to answer a single question or reveal one we hadn't thought to ask. When you see those brilliant, color-rich space photos, know this: they're not just pictures. They're stitched mosaics of filtered light, translated from data. They are paintings made from physics. So the next time you look up, remember, someone, somewhere, is already looking farther. And the sky is not just watching us back. It's telling a story we're still learning how to read. The truth about space debris and how much is really up there. The truth about space debris and how much is really up there. This is space debris, and it's more than just a mess. It's a growing problem. Since the dawn of the space age in 1957, humans have launched over 6,000 rockets and placed more than 15,000 satellites into orbit. Not all of them came back. Many died in place as some exploded, others collided, and every time they left behind fragments, sometimes just a flake of paint, sometimes an entire booster stage. Right now, there are an estimated 100 million pieces of debris orbiting Earth. Of those, about 34,000 are large enough to be tracked from the ground, traveling at speeds of over 27,000 kilometers per hour. At that velocity, even a bolt can punch a hole through a spacecraft. The International Space Station occasionally performs maneuvers to dodge incoming debris. And in 2009, 2 satellites actually collided, creating a cloud of fragments that still circles the planet today. Some pieces burn up in the atmosphere eventually, but many don't, especially those in geostationary orbit, over 35,000 kilometers up of Earth, where they can remain for centuries. Agencies like NASA, ESA, and even private companies are now working on solutions. Harpoons, nets, drag sails, magnetic capture. The goal isn't just to clean the sky, it's to keep access to space safe for the future. Because space isn't endless when it comes to orbit. There's only so much room around one small planet. So as we fall asleep tonight, let's picture it. A silver thread around the world, not of stars, but of fragments. A man-made constellation, glimmering, spinning, forgotten, but still there. The astronaut who brought a piece of the moon home in his pocket. Sometimes, space isn't about the machinery, it's about the moments. And this one begins with dust, ancient, gray, and silent. In 1971, during the Apollo 15 mission, astronaut David Scott walked on the surface of the moon. It was his third spaceflight, but his first chance to step onto another world. With him, a small rake, a camera, and a geologist's trained eye. Unlike earlier missions, Apollo 15 was designed for science. The astronauts spent longer on the surface, brought a lunar rover, and collected over 77 kilograms of moon rock and soil. But Scott wanted more than just numbers. He wanted something personal. In a quiet moment near the lunar module, he slipped a small rock, no bigger than a coin, into a zippered pocket in his suit's leg. Not to steal it, not to sell it, just to bring it home separately. He later gave it to his daughter, not as a souvenir, but as a way to connect her to something real, something timeless. NASA was strict about samples, and technically, the rock still belonged to the government. But no one reprimanded him. The gesture was too small, too human. Today, that tiny stone sits in a private collection, nestled among family photos and childhood art. It's a fragment of another world, touched by sunlight that never filtered through Earth's air. It reminds us that behind every mission patch and checklist is a person, someone who misses home, who worries, who hopes, someone who, when given the chance, picks up a rock and thinks of someone they love. The moon is far, but the people who walked on it, so they were never more human than in the moments like this one. What space weather actually is and why it matters. We check the weather before going outside, but there's another kind, silent, invisible, and it comes from the sun. It's called space weather, and it doesn't bring rain. It brings radiation, plasma, and magnetic storms. The sun is not calm. It seethes with energy. Every few days, it releases bursts of charged particles in an event called a solar flare. Sometimes, those particles are carried outward in massive waves, coronal mass ejections, or CMES. When these waves hit Earth's magnetic field, they can do incredible things. Sometimes it's beautiful. The aurora borealis, northern lights, dancing across polar skies. The particles energize atoms in our atmosphere, painting the night in green and violet. But other times, the effects are more dangerous. Strong space weather can knock out satellites, disrupt GPS, interfere with radio signals, and even damage power grids on Earth. In 1989, a solar storm knocked out electricity across Quebec, plunging millions into darkness. And in 1859, the Carrington event, the most powerful solar storm on record, caused telegraph wires to spark, catch fire, and continue operating after being unplugged. Today, with our growing reliance on satellites for weather, banking, communications, even farming, space weather matters more than ever. That's why NASA, NOAA, and the European Space Agency monitor the sun constantly. Special satellites like SOHO and Parker Solar Probe watch for flares, and measure the speed of solar wind. Sometimes we have hours, sometimes just minutes. There's no way to stop space weather, but we can prepare for it. And the more we explore beyond Earth, the more critical that preparation becomes. So next time you see a glowing aurora or use your phone's location, remember, the sun is always reaching out, and sometimes space sends storms. The dark side of the moon, why it's always hidden. Let's turn now to something familiar and mysterious, something we've seen in the sky our entire lives, and yet we've only ever seen one face. The moon is Earth's constant companion. It spins, it orbits, but it does something unusual. It always shows us the same side. No matter when or where you look, that familiar pattern of craters and shadows never changes. So what's on the other side? The answer isn't magical, it's mechanical. The moon is tidally locked to Earth. That means its rotation and its orbit take the exact same amount of time, about 27.3 days. So for every full spin on its axis, the moon completes one lap around our planet. It's not that the far side never sees sunlight. It does. In fact, it gets just as much light as the near side. But from our perspective, we never get to see it unless we send a spacecraft. The far side is more rugged, with fewer seas and more craters. It's harsher, older, less familiar. In 2019, a Chinese lander, Chang'e 4, became the first mission to soft land on the far side, revealing photos of a world that had never been seen from the surface. For decades, people called it the dark side of the moon, not because it's unlit, but because it's unknown. And perhaps that's what made it so poetic. A face turned away, keeping its secrets just out of view. Now we know what's there, but the feeling remains. That sense that something is always hidden, just behind the curve. Not dangerous, not mythic, just quiet. What would happen if Earth stopped spinning? The stars above us drift slowly each night, but they don't move. We do. Earth is spinning, always has been. But what if it stopped? It's the kind of question a child might ask, or the kind you think about in silence just before sleep. So let's go there. Right now, Earth spins at about 1,670 kilometers per hour at the equator. You don't feel it, but it shapes everything, day and night, wind patterns, ocean currents, even the shape of the planet itself. If Earth were to stop suddenly, instantly, the results would be catastrophic. Everything not nailed down would keep moving at that same speed. Oceans would surge, cities would crumble, the atmosphere itself would keep rotating, triggering global devastation in the first moments. But let's imagine something gentler. Let's say Earth gradually stopped, slowed over millennia until it no longer rotated at all. A day would no longer be 24 hours. It would be a year long. One side of the planet would face the sun in eternal daylight, scorching and dry. The other side, locked in darkness, would freeze, Only a narrow ring of twilight between them might remain habitable. Earth's magnetic field would weaken or vanish, since it's powered by the motion of molten iron in the core, motion tied to rotation. Without it, we'd be exposed to cosmic radiation, changing life as we know it. Tectonic activity, weather patterns, even timekeeping would all collapse into something new. A still world, a world of halves, light and dark, heat and ice. Of course, none of this is happening. Earth's rotation is slowing, but by just milliseconds per century. Still, it's humbling to realize that everything we know, morning, night, seasons, rhythm, depends on a quiet, invisible spin. And if it ever stopped, the silence would be profound. The oldest object we've ever touched. Let's turn now from motion to memory, not the memory of a person, but of the universe itself, of something far older than Earth, the moon, or even the sun. We're talking about stardust, and the oldest object humanity has ever touched is made from it. In 1969, a meteorite crashed near Murchison, Australia. Scientists collected its fragments and brought them to labs around the world. Inside, they found something extraordinary: grains of dust older than the solar system. How do we know? These grains are called presolar grains, microscopic crystals formed in the atmospheres of ancient stars. When those stars died, they scattered their contents across space. Some of that dust drifted for billions of years until it was caught in the cloud that formed our sun and planets. But some grains never melted. They remained intact, trapped inside larger rocks, and eventually they fell to Earth. By analyzing the isotopic ratios inside the Murchison meteorite, scientists determined that some of these grains were over 7 billion years old, older than our sun by more than 2 billion years. They are the remains of stars that lived and died long before our planet ever formed. They have no names, no story, just age. They are time in solid form. You can hold one on the tip of your finger, though you'd need a microscope to see it. A speck that predates the solar system, the Earth, and all living things. We like to think we live in the present, but sometimes the past falls from the sky, and when it does, it carries silence. So as you drift toward sleep, imagine it. A grain of stardust, older than time as we know it, resting quietly in a museum drawer, or floating still somewhere in the dark. Why do planets have rings, and why some lost theirs? We've held stardust in our hands. Now let's turn to something grander, not small, but vast. Not ancient by age alone, but by presence. Let's talk about rings. The halos around planets, the ornaments of gas giants. Most people know that Saturn has rings, wide, bright, unmistakable. But Saturn isn't alone. Jupiter, Uranus, and Neptune have rings too, thinner, darker, harder to see, but there. Even a few asteroids have been spotted with faint rings, held loosely by gravity. So, where do these rings come from? Most are made of dust, ice, and fragments, the remains of moons that shattered, or debris that never became a moon in the first place. They orbit in balance, too close to form a stable satellite, too far to fall inward. Rings are temporary. They may look eternal, but they're constantly shifting, colliding, fading. Some may last millions of years. Others may vanish within a few thousand. In fact, Saturn's famous rings, stretching hundreds of thousands of kilometers, might be very young. Recent data suggests they formed only 100 million years ago, possibly from a moon that drifted too close and was torn apart. And they're disappearing. In fact, Saturn's famous rings, stretching hundreds of thousands of kilometers, might be very young. Recent data suggests they formed only 100 million years ago, possibly from a moon that drifted too close and was torn apart. And they're disappearing. NASA's Cassini mission observed that Saturn's rings are slowly being pulled into the planet by gravity, raining down as icy particles, a majestic system dissolving into the clouds. So why don't all planets have rings? Some lost them. Some never had the right mass or circumstances. Some might gain them again if a moon is destroyed or a comet breaks apart too close. Rings are beautiful, but fragile. So as you drift off tonight, picture them, arcs of ice spinning in silence, remnants of chaos drawn into order, and someday into nothing at all. The Voyager record, what's actually on it? Let's end this part of our journey the way we started, with a message sent into the dark. You may have heard of the Golden Record, a gold-plated copper disc launched aboard Voyager 1 and 2 in 1977. But what's actually on it? The record was the brainchild of a small team led by Carl Sagan. Their mission: to create a message from Earth in case the spacecraft were ever found by another civilization or by no one at all. The contents are both precise and poetic. First, there are 116 images encoded as analog signals showing life on Earth, landscapes, DNA structures, people eating, animals moving, diagrams of atoms, planets, and human anatomy. There's a spoken greeting in 55 languages, including Sumerian and a child's voice in English, saying, "Hello from the children of planet Earth." There's a 90-minute playlist of music from Bach, Beethoven, and Stravinsky to Senegalese percussion and traditional Japanese flute. There's even Chuck Berry's Johnny B. Good, Just in Case. Also recorded, the brainwaves of a woman in love, captured as she thought about the wonder of connection and possibility. The cover of the record itself contains instructions like a cosmic decoder ring, how to play it, how to find Earth based on pulsars, and how to measure time based on the decay of radioactive hydrogen. It's both science and art, both map and message. Voyager 1 is now over 24 billion kilometers away, the farthest human-made object in existence. It drifts through interstellar space, alone, carrying a time capsule of who we were or hoped to be. And maybe one day, someone will find it. Or maybe not. But it doesn't matter. Sometimes, the most important part of a message is sending it at all. How Blue Origin plans to build in space. You've heard of SpaceX, of course, but there's another player, one that moves quieter but thinks just as big: Blue Origin. Founded by Jeff Bezos, Blue Origin's motto is Gratitium Ferociter, step by step, ferociously. Their vision goes far beyond launching satellites. They imagine a future where millions of people live and work in space permanently. And they're building the tools to get there. Let's start with New Glenn, a reusable heavy-lift rocket named after astronaut John Glenn. It's massive, built to compete with Falcon Heavy, and designed to land vertically, just like its cousin, New Shepard. But Blue Origin's most ambitious project might be something called Orbital Reef. It's a planned space station designed like a mixed-use development, part science lab, part hotel, part business park. Imagine floating offices, research modules, and panoramic views of Earth, all coexisting in orbit. Blue Origin isn't doing it alone. They've partnered with Sierra Space, Boeing, and even Amazon Web Services to handle everything from propulsion to data transmission. The long-term goal? To shift heavy industry off Earth, to mine and manufacture in orbit, to protect the planet by removing the messiest parts of civilization from its surface. Bezos often compares this vision to the early days of computing, when machines were big, expensive, and rare. Space, he says, is on the verge of its mainframe to laptop moment. Will it happen soon? No. But the foundations are being poured, in vacuum, in silence above our heads. So tonight, as you fall asleep, imagine not just a rocket, but a blueprint, steel and glass, anchored in zero gravity, step by step, becoming real. The coldest place in the known universe. We often think of space as cold, and it is, but not all cold is the same. Let's drift now to a place so still, so empty, that it holds the title, the coldest place in the known universe. And surprisingly, it's not far from Earth in cosmic terms. It lies within a constellation called Boötes, about 5,000 light years away. There, inside a large dying cloud of gas, is a strange object with an even stranger name, the Boomerang Nebula. Astronomers discovered it in the 1990s while studying cold gas clouds using radio telescopes. What they found defied expectations, a cloud that appeared to absorb background radiation, not emit it. It was so cold, it seemed blacker than space itself. When they calculated the temperature, they were stunned. Just 1 degree above absolute zero, negative 272.15 degrees Celsius. That's colder than the background temperature of the universe. Colder than empty intergalactic voids. Colder than Pluto, Neptune, or the shadowed craters of the moon. But how is this possible? The Boomerang Nebula is formed by a dying star that's ejecting gas incredibly fast. As the gas expands, It cools, just like air from a spray can feel cold to the touch. Only here, the cooling is extreme because there's no atmosphere to slow it down, no nearby stars to warm it up. It's the universe's own deep freezer. Eventually, the nebula will warm up. The star will stabilize, and the gas will begin to glow. But for now, it floats in stillness, a ghost of a star wrapped in perfect chill. So as you settle under your blanket tonight, think of this place, a cloud colder than space itself, a breath of ice drifting through the dark. The Mars that used to be rivers, lakes, and lost air. Tonight, let's visit a place you think you know. The Red Planet. Cold, barren, lifeless. But it wasn't always this way. Once, Mars was blue. Billions of years ago, the planet had a thicker atmosphere protected by a magnetic field. Temperatures were warmer, and across its surface flowed rivers, carving valleys, feeding lakes, possibly even filling seas. We know this not by imagination, but by evidence. Orbiters have photographed ancient riverbeds, twisting channels that end in deltas, just like on Earth. Rovers like Curiosity and Perseverance have found rocks that only form in liquid water, clay minerals, rounded pebbles, salt deposits. Even craters once thought empty have turned out to be ancient lake beds. Places like Jezero Crater, where Perseverance is now searching for signs of past life. But what happened? At some point, Mars lost its magnetic field. Without it, solar wind stripped away the atmosphere. The air thinned, temperatures dropped, water evaporated or froze. Now only traces remain: ice under the surface, polar caps, and possibly briny underground lakes still hidden in the dark. The Mars we see today, dry, dusty, red, is not the Mars that was. It's a world that remembers water, but can no longer hold it. And yet, we're drawn to it, not just for what it could be, but for what it was. Because in every dry channel, every salt crystal, there's a whisper. I was alive once. I had clouds. I had rain. As we plan missions, rovers, and someday people, we're not just exploring Mars. We're trying to bring it back, to understand how it changed and what that change says about us. So tonight, fall asleep under your own blue sky and dream of one that Mars once had too. The Saturn hexagon, a storm that shouldn't exist. Let's move now to the edge of mystery, to a shape spinning above a planet no one has ever walked on. Saturn, the second largest world in our solar system, is known for its rings. But high above its north pole, there's something else, a storm, and it's shaped like a hexagon. Yes, 6 sides, perfectly straight, perfectly stable, each side longer than Earth itself. A giant atmospheric vortex, first discovered by NASA's Voyager mission in the early 1980s, and it's still there today. Most storms form spirals, chaotic swirls. But this one is different. Why? Scientists believe it's caused by fluid dynamics, the result of jet streams interacting with the atmosphere at different speeds. In lab experiments, researchers recreated similar patterns by spinning liquids inside rotating cylinders. But Saturn's storm isn't small. It's 30,000 kilometers wide, deeper than Everest is tall, and spins at speeds of over 320 kilometers per hour. It has been raging for decades, possibly centuries, and no one knows exactly why it holds its shape. It pulses with colors: gold, blue, sometimes green, depending on the season. Cassini's close-up images revealed shadows, depth, and a swirling eye in the center, like a hurricane. But unlike hurricanes, it doesn't move. It simply spins in place, locked to the planet's rotation. There's no other known storm like it in the solar system. It's hypnotic, elegant, and slightly unsettling, nature forming geometry at planetary scale. So as you drift into sleep, imagine standing far above the rings, looking down at a pole crowned with a hexagon, a six-sided storm drawn in clouds, spinning forever in silence, a shape too perfect to ignore, and too strange to fully explain. How long could you survive in space without a suit? Let's imagine something unsettling. A person floating in space. No helmet, no suit, just the human body, exposed to the void. What happens, and how long would you survive? First, forget what you've seen in movies. You wouldn't instantly freeze. You wouldn't explode, but you also wouldn't last long. Space is a vacuum. There's no air, no pressure, and no way to breathe. The moment your helmet came off, the oxygen in your blood would begin to drop. You'd lose consciousness in about 15 seconds, not from pain, but from lack of air. You wouldn't suffocate in the usual sense. You'd simply black out. Your body would swell, but not explode. The skin is strong enough to hold it together. Saliva would boil on your tongue, not from heat, but from the lack of pressure. Tiny gas bubbles would form in your bloodstream. Your eyes would dry instantly. And after about 90 seconds, permanent brain damage would begin. If no one pulled you back in by the 2-minute mark, you'd die. But here's the strange part. It wouldn't be loud. It wouldn't be fiery. It would be quiet. No wind, no scream, just silence. Absolute and complete. NASA has tested vacuum exposure on animals and even humans during accidents in training chambers. In one case, a technician passed out and was safely revived after 25 seconds. He later said, "The last thing I remember was the moisture on my tongue starting to boil." So how long could you survive in space without a suit? About 60 to 90 seconds if someone finds you. And if not, you'd become one more silent satellite, drifting slowly toward nothing. How we found a planet by watching it blink. Not every discovery begins with noise. Some begin with the softest flicker, a tiny dimming in the light of a star, barely noticeable unless you're watching carefully. That's how we found our first exoplanets, not by seeing them directly, but by noticing when their stars seem to blink. This method is called the transit method, and it's beautifully simple. When a planet passes between its star and us, it blocks a small portion of the starlight. The dip in brightness is tiny, often less than 1%, but detectable, especially if the same dip happens again and again at predictable intervals. Each time the planet orbits, it creates a pattern, a signature, and from that flicker of light, we can calculate the planet's size, orbit, and even hints of its atmosphere. This method became powerful thanks to missions like Kepler, launched in 2009. Kepler stared at over 150,000 stars, capturing brightness data constantly. It didn't move, it just watched. And from that watching came thousands of discoveries, new worlds, some hot, some cold, some Earth-like, some entirely alien. The blink of a star told us that planets are everywhere, not rare, not distant, common ... Almost every star you see in the night sky may have its own solar system. We've since refined the method with missions like TESS and with ground-based observatories. We now even use it to study atmospheres as light filters through alien skies, revealing the chemical makeup of distant air. So next time you look up at a star, know this: it may have blinked once, and in that blink, it told us a secret. A planet, orbiting far from us, but not beyond our reach. He's Space Hotel, what it could actually be like. Let's imagine something that sounds like science fiction, but is slowly becoming real. A space hotel, not a research station, not a rocket. A place to stay, to sleep, to wake up with Earth floating outside your window. Several companies have already proposed designs, rotating structures, orbital rings, inflatable habitats. Among them, Voyager Station, Bigelow Aerospace, and Blue Origin's orbital reef. Some plan luxury, others research. All of them imagine a future where space is not just visited, but lived in. So what would it be like? First, the view. Through reinforced dome-shaped windows, you'd see Earth turning silently. Sunrise and sunset every 90 minutes. The sky always black, even at noon. Inside, you'd feel weightless, unless artificial gravity was created by slow rotation using centrifugal force. You'd float between your beds and the dining area. Meals would come in sealed packages, not freeze-dried paste, but real food adapted for 0G. Showers? Not likely. Instead, air jets, warm towels, or sonic cleaning. Toilets? Well, they'd work by suction, not glamorous, but effective. There might be a gym, not to get fit, but to prevent muscle loss. On Earth, gravity works your body without effort. In orbit, you have to fight to stay strong. And then there's silence. Space is quiet. No birds, no cars, no wind. Just the hum of circulation fans, radios, and your own breath. Rooms might be small, sleep pods, fold-down bunks, but the experience, vast. The first guests will likely be researchers, scientists, or wealthy adventurers. But one day, space hotels may be as normal as airplanes once were, and staying in orbit could feel routine. So tonight, close your eyes and picture it. A room in the sky, and you floating, smiling, drifting gently to sleep between the stars. The stars that orbit nothing, rogue suns in the void. We often imagine stars in families, gathered in galaxies, arranged in spirals, held together by gravity. But not all stars stay home. Some are alone, not orbiting a center, not bound to a system, just drifting through the dark. These are rogue stars, sometimes called intergalactic wanderers. They travel between galaxies, alone and unanchored. How do they get there? Often it begins with violence. A collision between galaxies can fling stars outward like sparks from a grinding wheel, or a supernova can kick a companion star free, a slingshot escape from a system that no longer holds it. Once unbound, the star moves in a straight line, no orbit, no sun, no home, just motion through intergalactic space, a place so empty the next star might be millions of light years away. Some rogue stars are fast, very fast. Hypervelocity stars, shot from the center of galaxies after close encounters with black holes, can reach speeds of 2 million kilometers per hour. They leave their galaxies entirely, exiled but not destroyed, as others drift slowly, quietly. Old red dwarfs, burning dimly for billions of years, unnoticed in the void. We've found a few, but most we'll never see. They're too faint, too far. Their light doesn't reflect. Their stories go untold, and yet they exist. Proof that not everything in the universe is part of a pattern. Some things just float. So tonight, as you settle in, remember, not all stars belong to a galaxy. Some wander, and in their wandering, they light a different kind of path, one that goes nowhere and everywhere at once. The rocket that turned around mid-flight and landed. For most of history, rockets were one-way machines. They lifted off, did their job, and fell back, in pieces, in oceans, or in flames. But that changed. In 2015, something happened that looked impossible. A rocket launched, then turned around mid-flight and landed upright. The rocket was a Falcon 9 built by SpaceX. Its mission was to deliver a payload into orbit, which it did. But then, instead of burning up in the atmosphere, the booster flipped, slowed down, and began its descent. It passed through fire, re-entry burns, slowing its fall. It extended its landing legs, fired one last engine burst just above the ground, and landed, gently, like a pencil balancing on its eraser. It had left Earth and returned to it. This maneuver is called a propulsive landing. It's incredibly difficult. The rocket has to adjust for wind, speed, fuel limits, and target drift. The margin for error? Less than a parking space. It took multiple failures to get it right. Crashes, tumbles, explosions. But each time, the data improved, and eventually, it worked. Now landings have become routine. Falcon 9 boosters have flown more than a dozen times each, and new rockets like Starship are being designed to do the same, but bigger. Why does it matter? Because it makes space cheaper, cleaner, repeatable, like reusing an airplane instead of building a new one for every flight. But there's something poetic here too. A rocket that doesn't just leave, it comes home. So as you drift off tonight, imagine the fire and silence of that return. A machine built for escape, choosing instead to fall with precision, to land, to wait, to fly again. What it would feel like to walk on a gas giant. Let's end tonight's journey with a question that can't be answered by a mission or a probe, only by imagination. What would it feel like to walk on a gas giant? Planets like Jupiter and Saturn are massive, bigger than all the other planets combined. But they're not made of rock. They have no solid surface. So how could you walk there? Let's suppose you tried. First, your spacecraft descends through thick, endless clouds. At first, it's calm, pale bands of hydrogen and helium. You're floating, drifting. You pass through storms larger than Earth, including Jupiter's Great Red Spot, a hurricane that's been raging for centuries. As you go deeper, pressure builds. The light fades. Clouds turn to mist, then haze, then crushing fluid. There's no surface to land on, only layers. The gas thickens until it becomes liquid metallic hydrogen, a state of matter that doesn't exist on Earth. It would feel like diving into an ocean of lightning. The pressure here is immense, over 2 million times greater than Earth's surface. Your body, your ship, your thoughts would be compressed into silence. And below that, a core, maybe. Maybe not. We're still not sure. But one thing is certain. You wouldn't walk. You'd fall, and fall, and fall. For hours, days maybe, until physics and time lost meaning. And yet, there's wonder in the imagining. Because even knowing you can't walk on Jupiter doesn't stop you from wondering what it would feel like if you could. So as your breath slows and your mind begins to drift, picture this. A descent through clouds no one has touched. A silence thicker than stone, and a step that never lands. Jupiter's most extreme storms, cyclones bigger than continents. Jupiter, the largest planet in our solar system, is a world of extremes. Its storms don't roll in gently, they roar. Most people know about the Great Red Spot, a massive storm larger than Earth, spinning for over 300 years. But that's just the beginning. Jupiter is wrapped in jet streams that blow in opposite directions, layered like ribbons around the planet. These bands create turbulence, and from that chaos rise cyclones, spinning vortices, many of them clustered around the planet's poles, each one larger than a continent. In 2016, NASA's Juno spacecraft flew over Jupiter's North Pole and revealed something astonishing. A perfect octagon of cyclones, 8 massive storms arranged in a ring with a 9th in the center. Each storm is over 4,000 kilometers wide, and they're stable, locked in place by invisible forces. At the South Pole, a hexagon of cyclones, patterns in chaos, weather drawn in geometry. But Jupiter doesn't just rage with wind, it glows. The planet produces auroras, far stronger than anything on Earth, powered not by sunlight, but by radiation belts and magnetic forces so intense they could fry a spacecraft's electronics in seconds. It's a planet made not of rock, but of storm, clouds of hydrogen, rain made of helium droplets, and lightning that flashes 1,000 times more powerfully than anything on Earth. Yet from a distance, Jupiter seems calm, banded, striped, elegant. That's the paradox, beauty born of violence. And as you drift to sleep tonight, imagine it, a world wrapped in endless storms, a sky of spinning giants, and silence beneath the thunder. The mystic mountain where stars are still being born. Let's travel 7,500 light years away, not in distance, but in wonder. There, inside the Carina Nebula, floats a formation known as the Mystic Mountain, a vast pillar of gas and dust, rising 3 light years tall, sculpted by radiation, gravity, and time. It looks like a mountain, jagged, shadowed, towering. But it isn't solid. You could fly through it like smoke. This is a stellar nursery, a place where stars are born. Inside, gravity pulls gas together, squeezing it until atoms fuse and fusion ignites. A star is lit, but the birth isn't gentle. Newborn stars blast their surroundings with ultraviolet light and stellar winds, carving the cloud into shapes, peaks, pillars, and caverns. The Mystic Mountain is both being created and destroyed. Its beauty comes from the tension between formation and erosion, a moment caught between before and after. What we see today is already past. The light reaching us began its journey before the pyramids were built. before language had writing, before time as we know it was measured. We see it now, but the nebula has already changed. Inside the shadows are protostars, not yet stars, but on the edge. Some may never ignite, others will become suns. Each will have its own story, its own system, its own gravity. And in 1 billion years, one of those stars might have planets, and one of those planets might have someone looking back. So as you close your eyes tonight, think of the mystic mountain, a cloud sculpted by stars, hiding more stars inside, a place where light begins, in silence, in darkness, in dust, and where everything bright was once invisible. The Keyhole Nebula and the wild magnetic fields of Carina. Not far from the Mystic Mountain, within the vastness of the Carina Nebula, lies a darker, denser region known as the Keyhole. It's not a star, it's a shadow. The Keyhole Nebula is a small, cold pocket inside a storm of light, dense gas, thick dust, a silhouette inside brilliance. It looks like a dark bubble, but inside, invisible forces are at work. Because this region is threaded with magnetic fields, not just static lines, but twisting, curving, shifting strands of magnetic energy that shape how gas flows, how stars form, and how matter moves. These fields are not visible to the eye, but astronomers have mapped them using polarized light, detecting how dust grains align with magnetic currents. What they found is astonishing. The filaments bend, ripple, and sometimes twist into loops. They act like scaffolding, guiding star birth, or like nets, trapping gas until pressure bursts. This magnetic architecture is delicate, too weak to feel with your hands, but strong enough to shape solar systems. Inside the keyhole, stars are still forming, but not freely. They push against the invisible, and the invisible pushes back. We used to think of nebulae as clouds. Now we know they're living structures, not alive like us, but active, reactive, full of motion and memory. One day, this dark region will be torn apart by the stars it helped create. Its shape will vanish, but the stars it made will keep burning for billions of years. So as you fall asleep tonight, think of the keyhole, a dark room inside a brighter house, silent, magnetic, ancient, and full of stars we haven't seen yet. Why there might be life inside gas giants. We often imagine alien life on rocky planets like Earth or Mars. But what if we've been looking in the wrong places? What if something lives inside the clouds? Let's talk about gas giants like Jupiter and Saturn, planets made mostly of hydrogen and helium with no solid surface, no ground to stand on, just endless atmosphere stretching for tens of thousands of kilometers. It sounds impossible, but maybe, just maybe, life doesn't need land. Some scientists believe that life could exist in the upper layers of these atmospheres. Not life like us, but floating organisms adapted to high pressure, low temperature, and chemical storms. They imagine microbial balloons, tiny sacs of gas that float, drift, rise, and fall on convection currents, feeding on sunlight, methane, or the rich soup of molecules found in these clouds. It's not fantasy. Here on Earth, we've found extremophiles, microbes that survive in boiling acid at the bottom of the ocean or inside nuclear reactors. If life can exist there, why not in a place like Jupiter? We already know that Jupiter's atmosphere contains organic compounds, lightning, cloud layers, and complex chemistry. It's dynamic, chaotic, alive with motion. Of course, we haven't found life there, and maybe we never will. But missions like JUICE and Dragonfly will soon explore other gas-rich worlds like Ganymede and Titan, searching for clues. And maybe one day we'll send a probe not to land, but to float, to dive into the clouds and listen for chemistry that whispers, "I'm here." So as you sleep tonight, imagine drifting through a golden sky and something drifting past you just for a moment. The Voyager probe that's now in interstellar space. In 1977, a small spacecraft was launched from Earth. It carried no crew, no return plan, just instruments and a golden record. Its name was Voyager 1. More than 4 decades later, it's still flying, still working, and now it's farther from Earth than any human-made object in history, over 24 billion kilometers away. Voyager has crossed a boundary few imagined it ever would. It has entered interstellar space. This means it has passed beyond the heliopause, the edge where the solar wind, the constant stream of particles from our sun, loses its power. Beyond this, the environment is shaped by forces from other stars. It is the space between solar systems. Out there, the temperatures are near absolute zero. Sunlight is a memory, weak, distant, nearly gone. But Voyager still moves forward, sending home data from instruments now older than most people alive today. It records cosmic rays, interstellar magnetic fields, plasma density. We are still learning from it, even now as it drifts silently through a sea of darkness. And inside the probe is a message. The golden record. It contains greetings in 55 languages, images of our planet, a baby's cry, the heartbeat of a young woman, songs of joy, sorrow, and everything in between, from Bach to Chuck Berry. It's a time capsule of humanity, not just what we are, but what we hoped someone might understand. One day its power will fail, the last signal will fall silent, but Voyager will continue on for millions of years, drifting among the stars, carrying our story. So tonight, as you close your eyes, imagine it. A spacecraft, alone in the dark, holding a whisper from Earth. Still going, still ours. How your body would change in zero gravity. Imagine waking up and there's no ups at all. In space, your body begins to change, not suddenly, but steadily, hour by hour, day by day. The most obvious change is height. Without gravity pulling down on your spine, the discs between your vertebrae expand. Astronauts can grow up to 5 centimeters taller, a gentle stretch that vanishes once they return to Earth. But that's just the beginning. With no gravity to pull blood downward, it redistributes. Faces puff up, legs slim down. It's called moon face, and it gives astronauts a round, flushed appearance. Nasal passages swell. Voices sound stuffy. Even taste can change. Bones begin to weaken, losing calcium and density. Muscles shrink, especially in the legs and back. Even the heart changes shape, becoming more spherical, pumping in a new rhythm against a body that's no longer standing. Eyes can change too. Some astronauts experience blurred vision due to fluid pressure inside the skull. It's not always permanent, but it's still a mystery we're trying to understand. And then there's balance. On Earth, your inner ear helps you know which way is down. In microgravity, that signal fades. Astronauts often report a strange sensation, like their body isn't where it should be. It's called space adaptation syndrome, a quiet confusion of motion and orientation. But the most curious part? Eventually, this becomes normal. The brain rewires, muscles adjust, the body adapts, weightlessness becomes home. And when astronauts return to Earth, walking is difficult, standing feels heavy. The body must remember gravity again, slowly. So tonight, as you rest in bed, think of this: a body floating, shifting, learning a new way to exist, and proving, silently, that humans are made to adapt, even among the stars. The planet that rains iron. Some worlds are too strange to imagine and too real to ignore. Let's visit a place where the skies burn and it rains metal. This planet is called WASP 76b. It orbits a star about 640 light years away, and it's what scientists call a hot Jupiter, a gas giant roughly twice the size of our own, orbiting extremely close to its sun. How close? A year there's one full orbit takes less than 2 Earth days. And because it's tidally locked, one side always faces the star, and the other lives in permanent darkness. The day side reaches temperatures of over 2,400 degrees Celsius, hot enough to vaporize metals. On this side, iron turns to gas, rising into the upper atmosphere like steam from a boiling pot. But on the night side, temperatures drop drastically, and as the iron-rich air crosses from day to night, it cools and condenses and rains, not water, not ice, but droplets of molten iron falling through high-pressure clouds, hissing into denser layers below. We've never seen the rain directly, but astronomers using spectroscopy have detected iron vapor in the air and none on the night side. It disappears, it condenses, it falls. This isn't the only world like it. Other exoplanets may rain glass, sapphire, or silicates. But something about iron rain feels heavier, stranger, too violent to ignore, and too quiet to witness. So as you drift toward sleep, picture it. A planet scorched on one side, frozen on the other. A place where sunset brings not rest, but metals falling from the sky, and no one there to hear it. The silent collisions of ghost galaxies. We often think of collisions as violent, chaotic, loud, destructive. But in space, even destruction can be silent. Galaxies collide, not sometimes, not rarely, almost constantly. The universe is full of them, galaxies made of stars, gas, dust, and dark matter drifting through space at incredible speeds. And sometimes they meet. When two galaxies collide, their stars almost never touch. The space between stars is so vast, so empty, that even in a head-on crash, they pass through each other like ghosts. But the gravity remains. And that's where the transformation begins. Gas clouds compress, stars are thrown into new orbits, black holes spiral together, and in the chaos, new stars are born, sometimes thousands at once. Some galaxies are caught mid-collision right now. The antennae galaxies, NGC 2207, ARP 299, all tangled, stretched, glowing with newborn light. They look like torn silk in the sky. The Milky Way, our home, is on a collision course too. In about 4 billion years, it will merge with the Andromeda Galaxy. No explosion, no sound, just motion. A slow blending of stars over millions of years, forming a new, larger galaxy, Milkomeda. But not all galaxies are bright. Some are made mostly of dark matter, invisible to telescopes. And when these ghost galaxies collide, the stars don't shine, only gravity speaks. We detect them by the way they bend light, or how visible galaxies move around something we cannot see. So tonight, imagine this. 2 galaxies drifting through the void. No scream, no flame, no end. Just the quiet folding of space and the birth of something new. The hottest exoplanet ever found. Some planets aren't just hot, they redefine what hot means. Let's drift toward a world called KELLT 9b. It's located about 670 light years from Earth, orbiting a blue-white star that blazes far hotter than our sun. And KELT 9b doesn't orbit gently. It hugs its star so closely that a year, one full orbit, lasts just 36 hours. There is no sunrise or sunset, only day and night, each locked in place forever. The day side of KELT 9b reaches over 4,300 degrees Celsius, hotter than some stars. At these temperatures, molecules are torn apart. Even hydrogen struggles to remain whole. Iron, titanium, and other metals exist as vapor, stripped, scattered, and lost to the wind. And yes, this world has wind. Supersonic jets that sweep heat toward the night side, which is still glowing hot, but cooler by comparison. Even there, darkness doesn't bring relief. The planet is so hot that its atmosphere is evaporating, blown away into space, forming a long glowing tail, like a comet, but made of iron and heat. No surface, no clouds, no life, just energy. What's more, the star is young, and this planet might not survive it. In a few million years, KELT 9b could be gone, boiled away entirely, leaving only memory and data behind. We discovered it using the transit method, watching the star dim slightly as the planet passed in front of it. A blink from a burning world. So tonight, as you lie in the cool dark, think of this. A planet so close to fire, it glows. A world where night never truly falls, and where even atoms can't hold on. Could the universe loop back on itself? We often imagine space as endless, a straight line stretching forever in all directions. But what if it isn't? What if the universe loops? This is not science fiction. It's a real question in cosmology. And the truth is, we don't yet know the exact shape of the universe. There are three main possibilities. It could be flat, open, or closed. A flat universe extends forever, infinite without edges or curves. An open universe curves outward, like a saddle, expanding forever but thinning as it goes. And a closed universe, so that's the one that loops. Imagine sailing in a straight line across the ocean and eventually arriving back where you started without ever turning. In a closed universe, if you traveled far enough in one direction, you might return to your origin from the other side. It's like living on the surface of a sphere, but in 3 dimensions. There are no walls, no borders, just curvature so vast we can't detect it yet. Scientists look for clues in the cosmic microwave background, the ancient light left over from the Big Bang. They search for repeating patterns, like echoes, that could suggest space is folded. So far, the evidence leans toward flatness. But the universe is so large, we may only see a small patch of the whole, and maybe, just maybe, it wraps around in ways our minds struggle to grasp. So as you drift to sleep tonight, let your thoughts wander, not forward or backward, but around, because in a looping universe, every ending might just be a beginning in disguise.